Okay, so we just did LRAM, right? Now, remember, for LRAM, we just said, let's use that left endpoint for every single one, okay? But is that 100%, how confident are you in that answer? Not really, because, hey, it was going up, right? So what we could do instead is we could use the right endpoint. Rectangular approximation method. And we're going to call this RRAM. Okay, so let's do the same. Let's just repeat it here. Right? Sorry, that was off the screen for a second. Let's just repeat that, but start with the same thing. Draw all your verticals in, so you can kind of see your subintervals. Okay, but instead of making the assumption that we maintain the left endpoint's velocity throughout the entire subinterval, let's make the assumption that we use the right endpoints. And if we make the assumption that we use the right endpoints, okay, we make that assumption, okay, then for the first subinterval, interval number 1, okay, it has a length of 1 and a velocity of 3. So if for 1 second you travel with a velocity of 3, right, that would mean that you've traveled 3 feet. Okay? For subinterval number 2, right, if we are assuming that we're traveling at the right endpoint velocity, that means we are traveling at 6 feet throughout the entire subinterval. I'm going to have to extend this up here, right, so it's above, right, just like that. Okay, so for this, if we make the assumption that starting, right as this one ends, we jump up to a velocity of 6, right? We'll travel at 6 feet per second for 1 second. 6 feet per second for 1 second. Okay, that's going to be an area of 6 there. Okay. For the next subinterval, if we look at this, we're going to use the right endpoint. Notice it's on the right. That's what I'm saying is the right endpoint. Okay. Let's assume that we're going to travel at 5 feet per second throughout the entire interval. How long is that interval? It is 1 second long. So that's 5. Right? 1 by 5. The next subinterval, if we look at it, subinterval number 4, the fourth one. Okay, if we're going to travel at the velocity that's on the right there, okay, that's a velocity of 3 feet per second. How long do we travel there? This length, we're going to travel there for 2 seconds because it's going from 3 to 5. So it's 2 seconds. Right, so that's 6. The next subinterval, we're going to travel at this velocity of 8 throughout the entire subinterval. So, right, how long is it? 1 second long for 8. 1 second long, 8 feet per second. So we're traveling at 8 total feet. For the next subinterval, you're traveling at 9 feet per second throughout the entire subinterval because you're using the velocity that's on the right. 1 second at 9 feet per second. 1 second at 9 feet per second, you've traveled 9 total feet. For the last subinterval, you can see that it's a length of 3 seconds. Okay, we're going to travel at this velocity over here throughout the entire thing. That's a velocity of 13. So 3 seconds at 13 feet per second. Okay, we're going to be traveling 39 feet in that subinterval. Okay. So while with the last one we always made the assumption we're using the left endpoint and traveling at that velocity, for this one we're doing the right endpoint. Okay. We're going to again add all those together, right? 9, 14, 20, 28, 37, 67, 76. So the right endpoint approximation would tell us that we've traveled about 76 feet in this interval over these 10 seconds. So you can see that that's a much higher, right, for ourselves, but that makes sense because you can especially see that, like for this one, we use that larger one, right? We can see that the rectangles tended to be a little bit higher than the other one. Okay. So, I mean, this is all well and fine for ourselves, okay? But you might say to yourself, I don't think it just this doesn't seem feasible to me that it randomly jumped from one to the next, okay? And that's 100%, I 100% agree with you. So it seems more likely, and again, this is all, likeliness, that if we just extend that there's some kind of relationship, and let's just assume that they had some kind of, it was linear between them. And again, we're making an assumption there. Maybe it was curved. We don't know. We have no idea what happens in between because we have incomplete information here. Okay. So if I'm looking at this, what if you say, I think this is more likely? If you draw all of your verticals in, then draw those verticals, we get a whole bunch of trapezoids and a triangle on the end there. Okay, see how there's a whole bunch of trapezoids and then a triangle? Okay, so this is going to be called the trapezoid approximation method. Otherwise known as TRAM. Right? The book's not going to say that, but I guys call it TRAM because I feel like it's easier if we call it TRAM. Okay? For ourselves. So you can see that we made trapezoid shapes instead of rectangles there. Right? So being a trapezoid approximation method, right, we're going to do the area of each trapezoid, okay? So, I mean, sometimes the trapezoids become triangles. That's even easier. So let's talk about subinterval number 1. I'm just not going to write out subinterval. It's kind of long. But if I look at that, right, if I think about that trapezoid here, right, 1/2 base 1 plus base 2. So base, right, if we look at, well, the base 1 is 0, base 2 is 3, the length of the subinterval is 1, okay, so we get 3/2 for that. So, and if we just look at it like, hey, that's the area of the triangle, right, base of 1, height of 3, 3/2, right, and that really makes sense. Okay, if we look at subinterval number 2, right, this would be number 2, it has, right, again, the area of a trapezoid, 1/2 base 1 plus base, right? Maybe you forgot this. I'll write this over here. Trapezoid area, 1/2 base 1 plus base 2 times height. Okay? So if we look at it, right, our bases, again, are the parallel, so the parallel side. So we have a base of 3 and a base of 6 here. Its height is 1. So we have 9/2 there. Ourselves, okay, and then the next subinterval, 1/2 base 1 is 6, base 2 is 5, length of subinterval is 1, so we get 11/2. Okay, so you can see that we have some fractions because we have this 1/2 coming into play. It's kind of annoying that we have that, but it's just because we're being more precise and we have those. Basically, because we've put these slanted sides into it, it's going to happen. Okay, so for subinterval 4, right, 1/2, let's see, base 1 is 5, the beginning velocity is 5, the ending velocity is 3, right, and it happens for 2 seconds, so 8, cut in half is 4, oh, well, these kind of cancel each other out. Okay, next one, 1/2, the beginning velocity is 3, the ending velocity is 8. Nope, it has a length of an interval of 1, so that's great. We don't really need that, so it's going to be 11/2. Okay, next subinterval, right? Beginning velocity is 8, ending velocity is 9. Okay, what we're basically doing is and for each of these, we're averaging the velocities, right? Thinking about how long that's going to, take to happen. So 17/2. You can write it as a decimal if you prefer. Right, it's up to you. Okay. In the last subinterval, right, it's going to start with a velocity of 9 and with a velocity of 13, and that's going to happen over 3 seconds there. All right, so it's going to be 33. Okay. Again, we add all those together, right? And so these numbers are the area of each of these particular, which basically tells you how far it traveled in each of these subintervals, assuming that it was a linear relationship between the beginning velocity and the end velocity. Consider, it's again an assumption we're making. Okay. So we add those together, right? And so when I do this without a calculator, I just kind of do it piece by piece. So this is 12 halves are 6. I'm going to add these two together. 26 halves are 13. Okay, so 46 plus 8 is 54, plus 6 is 60, right? This is 5.5, 65.5. Hopefully I did all my math right there. Okay, feet, right? And then again, that's an approximation there, okay? So you can see that we started with 57 feet, then we had 76 feet, and then we had 65.5, okay? Now, here's the most here's the big connection that's going to help us, so we don't do this every single time, okay? Notice, right? This is the big takeaway, okay? That will save you tons and tons of time. Notice that trapezoids, right? You basically, if we look at the two rectangles we have, and let's draw that right on this right here, okay? So I'm going to draw put all your heights in. Everybody take a time. Put all your not your heights in. Put all your verticals in for your subintervals, okay? And then in one color, do the rectangular approximation. Do the left rectangular approximation method. Okay. So in pencil, I'm using that's the left endpoint approximation. Then take a different color, and for each subinterval, draw in the right rectangular approximation method. What it would look like. We're basically just repeating what we did in the first two examples. Okay. Now with the third color, draw in the trapezoid approximation method. Well, the trapezoid, we just connected those two. Okay, there's the top of the trapezoid. Notice that the trapezoids are cutting the right and the left in half. They're cutting it in half. What is it doing? It's averaging out. So hopefully this diagram shows you, right, this explains to you like, hey, look, the trapezoid is taking the piece that's above and the piece that's below, and it's kind of doing the halfway point. So in this case right here, right, the left endpoint gave us this, the right endpoint gave us this big one, and the trapezoid said, hey, let's just average those two out, right, for myself. Let's just take that error, take that difference, and cut it in half. Okay, so the big takeaway here is that the trapezoid is the average of LRAM and RRAM. Okay? And put that into equation form, that would mean that if you average, you take the two, you add them up, and then you divide by 2. Okay? So if we have, in this case, we had our LRAM is 57, and we had our RRAM is 76. If we take those two and add them and then divide by 2, in a not so shocking twist, we are going to get 65.5. Hopefully get 65.5, unless I added something wrong here, right? Let's see. So you can hear Moose in the other room. 66.5. Oh, I must have made a mistake up here. All right, let me just go check my work here. All right, so that's 46.54. Okay, let me just found my mistake. This was 14. All right, so that's 66.5. Sorry about that. Okay. All right. 66.5. Hey, there it goes. So it's just me making a careless mistake right there. Okay. Sorry about that. That's why I need to be teaching you guys. You guys are my fact checkers. You would have found that mistake for me. So anyway. Okay. So do you actually have to calculate trapezoid approximation method doing all this? No, you don't. If you've just done the LRAM and the RRAM, you can get the average, and that'll give you a trapezoid approximation method. And that's great. right? We can just do that, and we'll be very, very happy with saving ourselves all this fraction time. You see, I made a mistake on the fractions there, right? And excuse me, the more math work you have, the more likely we are to make mistakes.